Okay, so has anyone else had that experience where they sit down to write a talk, they know exactly what they want to say, they've given very similar talks before, they just need to grind through the slides, and you sit down and a whole different talk on a whole different topic comes out suddenly? No? Only me? Okay. So this is the talk I was supposed to give, and am still going to give. And when we're done with this one, you get to have the fun talk. Much more ranty than this one. This one will be informative. The next one will be ranty. You have been warned. This is partial derivatives of regular expressions. I've given variations of this talk before, so if you're thinking this sounds familiar, it probably is. This is the Haskell version, not the closure version. Some other improvements as we go along. So, by the way, no math will be required. If you have totally forgotten your calculus or never actually took calculus, that's okay. You won't have a lick of problems. So this is based on the paper Regular Expression Derivatives Reexamined by Owens, Reppy, and Turon. This is actually work that dates back from, I believe, the 60s when this stuff was first getting laid down. But it was forgotten for the longest time, and now I and several others are trying to unearth it and go, hey, this is a really neat way of doing things. So let me start with the all-important question, why do you care? Who cares about regular expressions or derivatives of them or anything in this at all? So this approach is different from your classic approach you may have been taught if you took a compiler course. It is much easier to understand, in my opinion, than classic NFA algorithms, which require a whole lot of build-up and then, for the payoff. It fully supports all your standard regular expression patterns. So anything you can do with your standard Java regular expression libraries and so on, you can do with this. And it allows all new constructs which you don't normally see in regular expression libraries, like and not, because they're hard to implement in NFA algorithms, so nobody does. They're easy to implement here. And it actually gives you similar or better performance. I've even seen some measurements that gives you better performance than the classic NFA approaches. So what is a partial derivative of a regular expression? Well, before I answer that, I want to answer a more basic question. What's a regular expression? I mean, we probably all have an idea in our heads. We're programmers. We've used regular expressions. It's, you have a string like this. This represents a possible A followed by a B followed by 0 or more C's. And you hand it to a library and it gives you back a code that will recognize whether a string matches this pattern or not. Right? Well, I want to do something a little bit different. Rather than looking at it as a string, I want to consider a regular expression as being the set of all possible strings it matches. Now, this set may be infinite, so this isn't how we're actually going to implement it. But this is a very useful sort of intuition pump for what I'm about to say, what I'm about to do. So thinking about it just initially in terms of the set of all strings it matches will make our life a lot easier. So at this point, it's fairly easy to define. The partial derivative of a regular expression R with respect to some character x in terms of the set of all strings it matches is just all the strings R matches that begin with the letter x with the letter x removed. So this is exactly as simple as you think it is, but let's work through some examples. So I have slides out of order, obviously. In terms of Haskell, the nice thing about Haskell is it works with infinite lists. So we can write code and it'll compile and it'll give us an intuition pump, but this isn't how we actually want to implement it, but it tells us very exactly what we mean. So a regular expression is just a list of strings, possibly an infinite list. We don't care. The partial derivative of the regular expression, the primes here, the apostrophes at the end, mean these are intuition pumps. I'm going to be replacing these with real definitions later in the talk. This is not the code you actually want to write. This is just something to think about. So the partial derivative is a regular expression and a character, and it returns a new regular expression. And this goes, if the list is empty, obviously the result is empty. If the list is not empty, if the first string is empty, we leave it because it obviously doesn't start, the empty string doesn't start with the letter X. If it does start with the letter X, we take everything except the first character and prepend it onto the rest of the list, working our way down the list. Otherwise, we just leave it off the resulting list. So let's work through by hand. Let's work through an actual example of how this works. So we have that example regular expression I showed you earlier, here spelled out as an actual list of strings. For the record, if there's an example regular expression, it will be the same regular expression, just different representations. So this is all strings that maybe start with an A or maybe don't, followed by a B, followed by 0 or more C's. So this is our standard regular expression. So what's the partial derivative with respect to A? Well, we look at the first string. It starts with an A. So we copy it to the result and remove the A. Second string doesn't start with an A, so it just gets left off. Third string starts with an A, copy it, remove the A, and so on. Fairly simple concept, right? So if our starting regular expression is this, our ending regular expression is this set of strings. It's a set of strings B, BC, BCCC, etc. Likewise, we can do the same thing with the derivative with respect to B. Again, this is all strings here that start with the letter B, so this string doesn't get copied because it doesn't start with the letter B. If it's just the letter B, it becomes the empty string. Otherwise, we remove the B off the front. So this will be the set of the empty string, C, CC, CCC, etc., etc., etc. The partial derivative of our regular expression with respect to the letter C is the empty set. It's fairly easy to prove. None of our strings, all of our strings are going to start with either an A or B. They're not going to start with a C. So we're just going to look at all of them and go, none of them start with a C, throw them all out. So, pretty simple. This is as simple as you think it is. Important concept here. The derivative of a regular expression is itself another regular expression. This makes sense when you think, even if you think about it in terms of your standard string representation of regular expressions, right? So the derivative of this string representation of a regular expression with respect to A is just B followed by 0 or more C's. And with respect to B, it's 0 or more C's, including the empty string, right? So the derivative of a regular expression so far we've just been doing the derivative with respect to a character. The derivative with respect to a string is exactly what you would think it is. We just iterate over the string, doing the derivative of each and accumulating the result as we go down the string, right? In Haskell, we have a very easy function to do this. It's called fold L, fold left. It just walks down the string, applying PDRE C prime with our regular expression. Note, in Haskell, strings are lists of characters, so I can just fold over a string, and it turns into a list of characters, and it accumulates the result. This works exactly like you think it does. There are no surprises here. So, what is the derivative of our example regular expression with respect to the string ABC? Again, we start with our initial regular expression. We take its derivative with respect to A. That's B, BC, BCCC, right? We take it, I've compressed it down here, take the derivative with respect to B. So note all the strings here start with B, so it'll just be all the B's are removed, so it's the empty string C, CC, etc. And then we take the derivative again with respect to C. Note the empty string doesn't start with the character C, so it gets left off. But again, we get an empty string when we take the derivative and remove C here. So again, we're going to get the set, the empty string C, CC, CCC, etc. Exactly what you think it is. So therefore, our derivative of a regular expression with respect to the string is just all of the strings that start with ABC with the ABC removed. So these two gets dropped off because they don't start with ABC. This guy becomes the empty string. This guy becomes just the C string, and so on. Exactly what you're thinking. Formatting problems here, obviously. This is the easy way to think about this is I simply filter my regular expressions. I forgot my primes. My regular expressions are infinite lists of strings. Then I can just filter for all strings which are prefix of the one I'm testing for, and then go through and just drop the initial so many characters. Right? So, bit of definitions here. If a regular expression contains the empty string, we call it accepting. We are in the accepting state of our regular expression. A reason for this, so we can test if we're accepting, is simply, is the empty string an element of our list of all possible strings, right? Where here, elem just looks for some A within the list of A's. If the derivative of a regular expression with respect to a given string is accepting, then the regular expression matches the string. This is why accepting is important. This is why we want to define this. Right? So we can apply a matches function, which takes a string and a regex and goes, does the string match the regex? By doing the partial derivative with respect to the string, and then go, is the result accepting? This is less interesting. Yes, this code basically evolves down to, does this string exist in our list of infinite strings? But I'm doing it a little bit weird for reasons when we actually do the real implementation, this will make much more sense. So, does the regular expression A question mark B C star match the string ABC? Right? So we calculate the partial derivative with respect to ABC. That's just the empty string C, 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 C. Right? Contains the empty string, right there it is. So yes, as expected, it does match. The regular expression does match the given string. Another example. Does the regular expression A question mark B C star match the string just A? Do a derivative with respect to the string A, which is the equivalent of just the character A, right? So that's B, BC, BCC. There is no empty string in this result. There are a lot of strings in here, but none of them are the empty string. So A question mark B C colon C star does not match A. Right? As expected, as we would expect. Here's another example. Does our regular expression match the string ACC? Well, none of our strings here start with the string ACC. They always want to start with either B or AB. So the derivative is the empty set. There's no output here. This is the empty list. Right? Important point. There is a difference between the set that contains only the empty string and the empty set. As programmers, this is very intuitive for us. There's a difference between the list containing one string, which happens to be the empty string, and a list containing no items whatsoever. Right? So since this is the empty set, the set does not contain a string. So no, our regular expression does not match the string ACC, as we would hope. Right? If the set of strings the regular expression matches is empty, then we go, this is the error condition. We have hit a point where it doesn't matter how much input left we have to consume, we're not going to match anything. So we call this the error condition. Right? And we can easily test for that. If it's the empty list, then we're done. Yes, it is an error condition. If it's anything else, we are not in the error condition. The error state is terminal. We can never add strings. When we do a derivative, we have as many results or fewer. We can never have more results than we start with. So once we get down to 0 results, we're done. Abandon all hope of matching ye who enter here. So let's look at an implementation, a better implementation than the infinite list of strings, which will work if you're willing to wait infinitely long for the calculation to complete. I want to start with a rant. It's not a true Brian presentation unless I get a rant in, damn it. So here's a rant. Languages and strings like printf, regular expressions, things like this suck, in my opinion. I hate them all, right? First of all, they tend to be write-only code. Because they're in strings, we want to be short, and all of the examples are short and simple and easy to understand, like the one I'm using. Of course, once you start using them in production, things get a little bit more hairy. I mean, it's totally obvious what this regular expression does, right? I mean, if you saw this in the code, you'd just be like, duh, okay, this is what this does.
This isn't the Perl meal.
By the way, this matches or tries to match URLs in text, just in case you were wondering. They are impossible to debug. Remember, I said it tries to recognize URLs in code. Tries is the important word here. Have fun debugging it. I certainly did. Have fun debugging that regex. Think it'll work? Take a miracle. They lack any sort of abstraction capability. Even Fortran and COBOL programmers can take code, common code that's called in multiple places, and pull it out into a routine and call it from multiple places. They have some, languages like Haskell have incredible abstractive capabilities. Languages and strings have none whatsoever. And for example, you'll notice I highlighted in red these common sub-expressions keep showing up. There's no easy way for me to pull those out, give them a name that might be meaningful to programmers who follow on, and then combine them together later on. Nope, just got to bang it out in a string and replicate code to an extent the COBOL programmers feel jealous. They are difficult to manipulate, to compose, to modify, to do any sort of higher level operations on. The best operation you got is string concatenation. Good luck. They are difficult for tools to analyze. Your compiler, if your compiler has any ability to detect errors, it loses it once it starts looking at languages and strings. And especially if you're using a language like Haskell, which has incredible tools for validating the correctness of your code, like type systems, gone. Welcome to stringly typed code. So that's my rant. Thank you for listening. So our solution, we're not going to do a language and a string. We're in Haskell. I'm going to use a variant type to implement an abstract syntax tree. So this is exactly as you would think I would do. I'm just going to have a data definition, and I'm going to start adding stuff to it, right? And we're going to end up with structures that look like this. So we have a follow, starting with an optional char, with another follow. A follow means one regular expression followed by another regular expression. Optional means a regular expression that may or may not be here. Char means recognize a given character. Many means recognize 0 or more of a given regular expression. So yes, once again, this is the same regular expression I've been using this entire slide. That's what we're going to end up with. It's a little bit more verbose, but you'll notice I'm getting the type checker to help me make sure I'm constructing stuff correctly. You can now write all sorts of code to manipulate this, to walk up and down the AST and do all sorts of transforms, etc. I'm going to leave as an exercise for the student, if you feel like it, to write the code that takes your language in a string and spits out one of my regular expression structures. So let's get started on some real code. So I have a data definition. And by the way, this is something I find myself doing a fair bit in Haskell code, and it actually works very nicely. So I know I need a data definition here, but I don't know what I want in it. So I just start with data regex equals something, and I will replace that something with the right stuff as I need it. And I know I'm going to want a pdrec function that has this type, takes a regular expression and a character, and it returns the partial derivative, right? But I don't know what the code is, so I'm going to fill that out later. I'm going to start with undefined. Undefined, by the way, is a value that has any type. For all A, it has type A, so it can be used anywhere. And when you try to evaluate it, it just throws an exception and goes, I'm undefined. So this is a useful way, by the way, to stub out your code in Haskell and to build things up and go, I know I want something here, but I don't know what it is, and I don't want to deal with it right now. So for the moment, it's undefined, and I will fill it out as I need it. So we can, using these base functions, which haven't been defined yet, build up our pdre function, which calculates the partial derivative of a regular expression with respect to a string, not a character. That works exactly the same as before. And you can also have the matches function, which takes a regular expression in a string and returns true if it matches and false if not. Right? Now, this stuff works exactly like before and exactly as you think it would. So let's start filling in the data. Let's start with error. Error represents the empty set. In our example, this would be like having a constructor, error prime, that returns ourselves the list of strings that matches, and it's just the empty list. So now I replace the something with regex equals error, right? The partial derivative of C, when it's an error, when the regular expression is an error, always remains error. Since this is the empty list, nothing can match, so the empty list goes to the empty list. Is the error state accepting? No, obviously. Is it the error state? Yes, obviously. Accepting. Starting with the trivial stuff here. We'll get into more interesting stuff in just a minute. This represents the set containing just the empty string. So in terms of our original intuition pump implementation of infinite lists of strings, this is just the list of the string, the empty string. Oh, wait, stop that. So, data regex. I'm going to start using ellipses here to represent everything else we've already added, plus, in this case, the new constructor accepting, right? I'm also going to just start listing the individual cases here. Obviously, you'll need to fold these in where they belong. The partial derivative of accepting with respect to any character is the error state. The empty string doesn't start with any character, it's the empty string, so it gets thrown away, and it's the only state in our string, so it's the error state. Is the accepting state accepting? Obviously. Is it the error state? Obviously not. Right? Char. The char constructor represents the set containing just one string, the string of one character. So in our intuition pump representation, char prime C is just the list of the string of one characters. Remember, strings are just lists of characters. So this is a string here of the character C. Right? So we add the char constructor to our regular expression data set. The partial derivative of char C with respect to a character x, well, if C and x are the same character, then it's going to be to the accepting state, because our one string starts with that character, so we'll remove it and it becomes the empty string, and so we're left with the list of just the empty string. If it's anything else, then obviously that string will be, our only string in the set will be just discarded, so we will go to the empty list, which is the error state. It is not accepting because it only contains one list, one string, which is not empty because it has the character C in it. Right? It is also not error because it does contain an element. So it is not error either. It's all working exactly as you think it does. Optional represents the set of everything contained in R plus the empty string. So we can always accept at that point. We can always skip over whatever the regular expression would match and just go, we accept where we are now. So in our list representation, our intuition pump, this is optional of a regular expression is just whatever list of strings we otherwise accept plus the empty string. We just cons the empty string on. Right? So we add our optional data constructor. This now takes a regular expression as its argument, notice. Right? The partial derivative of an optional R with respect to a character x, well, we know the empty string we added will just get thrown away. It won't start with the letter x because it's the empty string. So we can ignore the fact that this is an optional, and the partial derivative is simply the partial derivative of whatever R would be with respect to the character that should be x, not c. My apologies. Is it accepting? Yes, obviously it's accepting. We explicitly made it accepting. We explicitly added the empty string to the set of strings we match. Is it error? It is not. Even if R is an error itself, we have added the empty string to the list of strings we match, so it is not an error. So we don't even need to look at R. We don't care what R is. We know it's not error. Right? So just want to do a quick code review. Added a bunch of code, a bunch of simple cases, but I wanted to actually show you what the code is going to start looking like. So here's our data constructor as it exists right now. It's error or accepting or char of a character or optional of a regular expression. Right? Here is the definition of our PDREC function, which takes the partial derivative with respect to a character. Right? If it's an error, it goes to error. Accepting goes to error. Character goes to accepting if the characters match, otherwise it's an error. Optional goes to ignore the optional. And that should still be an X. Copy paste error. Our is accepting function is accepting error is false, is accepting true, is accepting char is false, is accepting optional true. Right, so this is how the code is starting to look. I just wanted to take a quick spin through so people could keep track of what's going on. And finally, is error has exactly the values you would expect. So let's start adding some interesting constructors here. So far, we've been fairly simple. Let's add the OR constructor. OR constructor represents the set containing all strings which are in R or S. And our intuition pump, which is just we list all the strings it matches, we can simply concatenate the two lists. So now we match everything, our list of everything we match is everything in R and everything in S. By the way, we are not keeping anything in any sort of order, and we're not worrying about duplicates here. This is just an intuition pump. So actually implementing this, we have the OR constructor, which takes two regular expressions. The regular expressions we're ORing together, right? The partial derivative with respect to a given character x is just the OR of the partial derivatives of the two subregular expressions. This makes sense when you think about it in string concatenation. If I could split it apart to the original two strings, I can just calculate the partial derivatives on those two lists of strings and then reconcatenate them together. Right? Is accepting. It is accepting if either subexpression is accepting. If either list contains the empty string, then it'll be the empty string will be into concatenation of the two lists. It is an error only if both subexpressions are an error. You only get the empty list out of concatenating two lists if both lists you're putting in are empty. If either list is not empty, then the result of the concatenation is not empty. So is error is only on AND. Speaking of AND, let's do AND. We've done OR, let's do AND. This is starting to get into interesting territory. Most NFAs will not let you do AND because they're really hard to implement, right? But our intuition pump is very simple. You got two lists of all the strings they match. The AND is all elements from the first list, which are also in the second list. So it's literally set intersection. OR is set union. This is set intersection. AND is set intersection of all strings we match, right? So the implementation, again, is very simple. We have our data constructor here, ANDing of two regular expressions, right? The partial derivative of the AND is, again, the AND of the partial derivatives of the two subexpressions. Again, this makes sense if you remember. If I could recreate the original two lists we intersected together, and then did the partial derivatives on the two lists, and then intersected the result, that is the same as intersecting as doing the derivative on the intersection, right? Is accepting. It is only accepting if the empty string is in both sublists. So both subexpressions have to be accepting. Because if the empty list is in one but not the other, it won't be in the intersection. Likewise, if either of the two subexpressions are in error, i.e. they're the empty list of all strings, then the intersection will be the empty list. The intersection with the empty set is the empty set, right? So this is how we do AND. So we've done OR and AND. Can we do NOT? Let's have real fun, right? NOT represents the set containing all strings which are not in R. So if I had some way to generate all possible strings, the list of all possible strings, and this would definitely be an infinite list, I just select out of it all strings that are not in R, and that is our NOT, right? So we have a NOT, we add a NOT constructor to our data regular expression, right? Which takes another regular expression. The partial derivative of NOT is, again, simply the NOT of the partial derivative of the resulting regular expressions. And that makes sense once you think about it in terms of lists of strings. Is accepting, if the empty string is in the set we're given, then it won't be in the negation of that set, and vice versa. So is accepting, we are accepting not R is accepting if R is not, and vice versa. Is error is an interesting case here. And I've done something wrong, but usefully so. So the only way not of some regular expression is an error if that regular expression matches all possible strings. That's actually hard to detect. You end up with Turing completeness there, basically. So I'm not even going to try because I'm lazy. And we only use error to early exits to go, we've hit a point of no return. We can always keep iterating on error and we get error back, so it doesn't matter. We're just using that as an efficiency, breakout of our loop early. So this is wrong, but it's usefully so. And right is way, way too hard. So let's flush some things out here. A couple of more combinators. Follow represents the set containing all strings which are the concatenation of some string in set R followed by some string in set X. Again, our intuition pump, it's X plus Y, where X is some string out of R and Y is some string out of S. Right? So we have a follow constructor here. Is accepting. Note, it's only accepting if the empty string is in both. Which makes sense because if the empty string is in both, one of the combinations we will pick the empty string out of both, concatenate that, and get the empty string out. The empty string, if one or the other doesn't have the empty string in it, we will never have an empty string. Empty string plus not empty string equals not empty string, right? And likewise, if either set is empty, we're automatically going to be in the error case. Because we're not going to have, remember, we have to take a string from A and a string from B. Well, if there are no strings in B, we're not going to have any combinations there.
What's the partial derivative?
Partial derivatives on the next slide because it's a little complicated. Partial derivative. Ask and ye shall receive. So the partial derivative of is accepting, so the partial derivative of follow R S, it's a little bit complicated because we have to go, is R accepting? Because if R is accepting, we can always skip over R and just go to S. So if R is accepting, it is either the partial derivative of R followed by S, or we can skip R entirely and just go, it's the partial derivative of S with respect to X. Right? If R is not accepting, then it is only the partial derivative of R followed by S. This makes sense. Think about it in terms of strings and lists of strings, and this does make sense. Right? Many represents the set containing the empty string or all strings which are the concatenation of one or more strings in R. This is basically zero, this is your Klein star, your X star in regular expression languages, right? So our intuition pump is either, it's the empty string followed by all combinations of concatenating strings in R. And I'll let you work out the code. It works out exactly like you think it does. So we add our many regular expressions, right? So when we're calculating the partial derivative of many, we can always replace many as an optional, many of R as an optional R followed by many of R. Right? So, but when we take the partial derivative, the optional just goes away. So we're taking the partial, when we're taking the partial derivative, it is always, we can always treat many R as R followed by many R. We can always pull an R out and start taking partial derivatives of it. Right? Which is exactly what we have here. It's the partial derivative of R followed by many R. Right? Questions? Nope. Is accepting? It is always accepting. We have defined it as always accepting. Zero implementation, zero iterations of R is always legal. Is it an error? Again, this is false, I believe, but usefully false. No, it's not. I take that back. Because we have explicitly added the empty string, it is definitely not the error. It has at least one string in it. My mistake. So, I want to take a pause here for a minute and address an issue that has probably came up. I've given this talk before, a variant of this talk before, using closure code. And I wanted to address why I was doing things the way I was doing things. And when I did the closure code, I did multi-methods. And I'm doing it in Haskell, I'm not using multi-methods. Now, multi-methods are function dispatched by, and you give it an accepts function basically that goes yay or nay. And it just literally iterates through all possibilities and go, do I call this one, do I call this one, do I call this one? So it's multi-dispatch that way. Normally via the shape, via the data structure. They are very slow, but they allow you to have open data structures. The downside of using variance types, I use variance types because this is example code and I wanted it simple and easy to understand. The downside is you can't add stuff. The user cannot add stuff to variance types. So the question is, can we do this in Haskell? Can we do something similar that allows us to have open data structures in Haskell? The answer is yes. You use a type class. We define a type class is regex, is any data type that has the functions pdrec, is accepting, and is error of these types, where R is these types. And you end up writing a lot of code that looks like this. Oh, sorry, we can use the type classes instead of our data type, explicitly doing the data types, and go, we can now match against strings, we can do, does a string match, we can do all of our usual stuff. You end up writing a lot of code that looks like this, and the formatting, the font size has changed because it's a different computer, and I apologize for the formatting. But your OR takes, in addition to taking two regular expressions, it takes two regular expression types. And we can go, if type R is a regular expression and type S is a regular expression, then the OR type of R and S is itself a regular expression and has exactly the definition you would think given the equivalency of the code before. So the answer is yes, you can do that in Haskell if you want to. I question the utility, but that's a different debate. So now we have the basics of a regular expression library, which supports all the standard regular expression patterns, and then some. I've given you the basics. There's obviously a bunch more you want to add if you were doing this for real. I'll let other people fill it out. Now we want to make it fast. This is much better than our infinite list. This will allow us to test whether a string matches a regular expression in finite time without having to deal with infinite lists and infinite computations on infinite lists. But it's still not very fast, especially when you compare it to like the Java or the C regular expression libraries, which are blindingly fast. You know, libraries like grep. Yes. Yes, parsec has the same problem. That if you're going, I mean, you can grep terabytes of data in reasonable, as fast as you can read it off the disk. Trying to do even atto-parsec against terabytes of data, and it'll be kind of painful. So I'm going for grep level speeds. I want to go, how fast can we make this sucker? So grep gets its speed from being a deterministic finite automaton, or DFA, or a state machine. So what is a DFA? A DFA is just a graph. You got a set of nodes and edges. The nodes are states. They represent, you've matched some set of the regular expression. The edges of your graph consume one character to transition from state X to state Y, right? So if you're in state X, there will be one edge that consumes character C and transitions. So if your next input character is C, if you're in state X, you go to state Y. You can only be in one state at a time. There is a non-deterministic finite automaton, I'll learn how to say that word one of these years, that lets you be in multiple states. The performance comes from you're only in one state. So for example, this is our example regular expression again. We start here in state 0, If we see if the first character in the string is A, we transition to 1. If the next character is B, we transition to 2. If the next character is C, we transition from 2 back to 2. And 2 is a double circle. That means we're accepting. If we're in state 2, we're happy, and we've matched the string. Right? So the advantage this has, we can represent, oh, and all, by the way, all other transitions are the error transition. If they're not explicitly stated, they're the error transition. So if you're in state 1 and you see the character A, well, there's no outgoing edge from state 1 that consumes the character A, so that's the error case. So if you saw the string A, we know it wouldn't match. The advantage this has, we can represent it as literally as a table. And we can go, here's our state, here's our input characters. And when you're in state 1, and you see input character B, you transition to state 2. And the second table here, that goes, are we in an accepting state or not? Only state 2 is true, everything else is false. Right? So this allows us to be blindingly fast because our matching code ends up, went too far, yes. Our matching code ends up looking like this. We read the next character from the input. We have what our current state is. We do an array lookup. This is, you know, a single memory load on most CPUs of our state and our character, right? And that gets us our new state. We repeat until we have no more input. And then we go, are we accepting or not? If our state is -1, that's the error state. We've fallen out somewhere. We're done. We stop reading input. As you might expect, this code on modern CPUs flies. It is incredibly simple. It is incredibly fast. Our CPUs are designed to implement this. They love it. So, converting a regular expression to a DFA. This is where your classic compiler theory gets a little bit hairy. And they start talking about Thompson's construction and all sorts of things. I'm going to explain it to you in one slide. Concept is really simple. For every state, we have an associated regular expression. That is the regular expression we had when we got to that state. So if we're in state X, we go and we want to know what states do we go to when we see character C. We take partial derivative of our current state with respect to character C, and we go, does that state already exist? Do we already have a state with that regular expression? If yes, the edge goes to that state. If no, we need to add a new state with the new regular expression associated with it. And we then just run for all possible states, for all possible input characters, we just run all the combinations. And that gives us our table. You're probably going to want, by the way, if you actually implement this, you're going to want to have a regular expression simplifier to deal with the regular expressions I compute are not optimal. So for example, or of error in something can be just replaced with the something. Not of something can just be replaced with something, etc. You'll want to write some sort of simplifier like that to do this. But other than that, the algorithm works exactly like you think. So we now have a DFA implementation of our regex. And we can use that really nice fast code and be able to match strings as fast as we can pull them off disk, just like grep can. So conclusion, derivatives of regular expressions are easy to understand, especially when you think in terms of the lists of strings and not more complicated data structures. They are easy to implement, especially in a language like Haskell. They allow implementing hard features which you don't often get, like and not. You find very few regular expression libraries that allow you to do and not of regular expressions. And can be as fast as normal regular expression implementations like grep. Right? And that's all I have. So, any questions on this? before we take a break, and then I get to do the fun one. Question, yes?
How can you be sure that when you actually try to bring it to the DFA, you don't actually have things that are equal, but they just keep growing and growing and getting more complicated stuff?
Well, part of that is your simplifier needs to be able to handle that and that's why I was saying you need a simplifier because it's well, most of the constructions are finite by construct, so they are going towards. There are a couple like many that will loop on themselves.
There's an algorithm on DFAs that can produce the minimal DFA. I think it's closed.
Yeah. There's only a couple. I mean, the general thing is there's only a couple of constructs you have to worry about. Follow being the big one, because remember, follow and many both can be a larger structure. The derivative can be a larger structure than you started with. The answer is you want to sort of look at the edge cases like that. I don't think there's or at least I don't know of an easy answer to go, here are the ones you absolutely need. Here are the simplifications you absolutely need to make sure you don't blow up. I think the answer is to actually try it and see. Yes?
One side comment on that. If you think of these, your regular expressions are basically rational functions. This is pretty Heisenberg way of doing calculus when you keep differentiating a rational function.
Yes. Any other questions, comments? Oh, question?
So you showed how you could implement some operators from significant values.
Yeah.
Expression libraries. Are there, so it seems like you're describing something that has like a level of power kind of in between traditional regular expressions, but not like at the level of context-free grammar.
No, these would be full regular expressions in the original sense of clean.
Yeah, in the
Not the whole other library component called clean is another story.
yeah the
Traditional regular expression libraries that don't have these capabilities are not full regular language implementations then?
What they call Unix is not the full regular language, far from it.
Yeah, and I will comment, there was going to be another section that didn't get written. There are regular expression libraries. The PCRE, Perl compatible regular expression library, has capabilities that I haven't shown you how to get here. Note, PCRE has the ability, you could write regular expressions in it that factor numbers into their into their two factors. So that should give you an idea of how powerful it is. Basically, where that comes in is, I haven't shown you how to make this. I have some ideas, I haven't actually tried them. You make this currently it's just here's a string, doesn't match yay or nay. We would like to expand it to do, to be able to do a functor or an applicative style thing where not only do we match a string, we produce some value based upon matching that string. And if we could then leverage that power up into being a full monad, that would give us the power of a Perl compatible regular expression, which is not going to be a full DFA, by the way, but I have some ideas on how to hack it. Talk to me at the bar tonight. I'm not sure how coherent that was, but hopefully it's something of an answer. Question?
Just to kind of add the answer to that previous question, a conventional regular expression library like prep or something actually is more powerful than real regular expressions, including this, as far as which things you can absolutely express. If you use prep as you want to do something with AM, you're going to have to write a very long and complicated regular expression, but you can expand it all out into just the things that prep has.
Yeah.
Like prep has back references, which lets you do the thing where you can write a expression that
Yeah. So that's also where Perl compatible regular expressions, PCRE, gets its power from. And it's the back referencing that gives you the power. But note, the back referencing also gets you out of DFA land. You cannot do that in a classic DFA. So it's going to have to be something more than that. And if people are interested, I think talk to me at the bar because it's a long rant.